Hi. The material I've been working on for my thesis is chromium thiophosphate. Well, at least one of the materials. I've been working with Los Alamos for a year now on this project because it is a very in-depth study. And although I'm only working the theory side of this project, we do plan to hand it over to SINT for their experimental procedures with this material. So this is actually a pretty good exercise for me to go through because I've only been doing theory for the past 4 years. And so this is going to cover what is actually happening behind the scenes after I hand over data. So 2D semiconductors can be grown through chemical vapor deposition. However, because chromium thiophosphate is a ternary compound, it must be grown through chemical vapor transport. After bulk crystals are grown, they can be extracted with scotch tape, and then the amount of layers can be identified through Raman spectroscopy. So we're going to look at these procedures in a little more detail with the presentation I have here. Before we get into the details of the production process, I think it's important to first establish the background, the foundation, and the motivation behind developing the understanding and production techniques for 2D semiconductors. Starting with some background on semiconductors, they're quite versatile in application, and their bandgap size is what dictates the unique properties of the material for use in their application. For example, cadmium sulfide is used to convert sunlight into electrical energy, and this is done through its wide bandgap. In contrast, indium arsenide has a narrow bandgap, and this allows it to be used for infrared photodetection. Transistors are most commonly used in everyday application and has become the basic building block of technology. And in a transistor, two types of semiconductors create a flow, allowing us to control in what direction electricity is being sent and also how much of it is being sent. So now the question that comes is, if these materials are so diverse, why do we need to continue studying them if we already have a plethora of uses for it? Well, if you're familiar with Moore's law, the geographical occupation of technology continues to grow with our advancements. Because of this, it is important to find materials that can behave similarly when reduced down in size. Currently, transistors cannot be reduced beyond a certain volume due to a quantum tunneling effect. So the search for atomically thin semiconductors has become a hot topic in the condensed matter physics area. So 2D materials are materials that can be thinned down to these sizes. Graphene was the first successfully exfoliated single layer of atoms due to its weak interlayer coupling, but it has a strong covalent bond due to the hexagonal shapes in it. And this is within the XY plane. And these strong bonds also allow flexibility within the application paired with that thin size. And this was a revolutionary discovery back in 2004. However, graphene is highly conductive. Thus, it is limited in application and cannot be used in transistors. So that brings us to the point where if nature can't develop it, then science will. 2D semiconductors can be produced through chemical vapor synthesis. This is usually carried out through chemical vapor deposition. However, ternary compounds are a special case, needing a well-controlled environment to successfully grow. So chemical vapor transportation is used for these. Once the crystals have grown in bulk, they can be exfoliated into their layered components by using the mechanical cleavage method, aka the scotch-tape method, in which the crystal sits on a substrate and the layers are extracted with tape by hand. And so now that we have a means of producing 2D semiconductors, they have been shown to have use as substrates, application in nanoelectronics and optoelectronics, and theoretically quantum computing because of their high electron mobility. Okay, moving on to the material focus, chromium thiophosphate. Chromium thiophosphate is a rectangular structure and paired through the covalent bond of phosphorus and sulfur 4, then ionically bonded with the transition metal chromium. If you take a look at the unit cell I have there, you can see the chromium sits in this octahedral geometry with sulfur, and each octahedral is connected by phosphorus. And then if you look between the phosphorus, you can see the hexagonal shape that creates those strong in-plane bonds, just like with graphene. Also, chromium is actually the first metal atom to sit in this octahedral with sulfur. So this material has been studied quite a bit over the years, but it has recently developed a lot of attention due to its use as a 2D magnetic semiconductor. The monolayer just got an air stability time published just a few months ago. And actually, my mentors got concerned about that publication because the DFT part of it was similar to mine. But of course, no lab is as thorough and accurate as Los Alamos, so they had a very thin amount of study done in the DFT section. So I did miss getting scooped by that study. Side note. Okay. All right, let's move on to the main topic of this presentation, the process of production for chromium thiophosphate. Now that we've covered the bonding process, we can cover how it binds together through the transport method. So chemical vapor transport is a process where the powdered solid is volatilized when in contact with a reactant in a gas phase that acts as the transporting agent. The powders are carried through a temperature difference in a vacuum sealed capsule where it will be deposited in the form of crystals over time. Specifically for chromium thiophosphate, this process takes a week to form a few millimeters of the crystallized compound, which is enough for the preceding exfoliation process. The powder sample is first readied as a ratio of 1:1:4 for chromium, phosphorus, and sulfur respectively. The atomic ratio is then annealed around 700 degrees Celsius. The ampule is made of quartz, and the process happens at a pressure below 3.5 times 10 to the negative 5 torr. The starting temperature is 750 degrees, and the gradient ends at 710 degrees. And actually, chromium thiophosphate doesn't need a transporting agent for the CVT method, and it still yields more than 60% of the starting powder, which is considered a high chemical yield. The powder is made by a ground in a mortar, and the quartz ampule is sealed at a low pressure by a turbomolecular pump and closed with a flamer. The temperature gradient through the ampule is warmed up in a special furnace called a 3-zone furnace. And then the sample is inserted into the ampule. The process is exothermic and is quick to happen for chromium thiophosphate, and you can actually see the vapors almost immediately during that process. So after a few days, the furnace is turned off and the sample is cooled with the furnace. The purest chromium thiophosphate sample is collected at the zone around 710 degrees, and at the 750 degree zone, chromium 3 sulfide powder is found along with some slag. So with the solid crystallized chromium thiophosphate bulk compound grown, the next step is to ensure it is the correct compound and ratio by using energy dispersive spectroscopy. This process is carried out using a high resolution scanning transmission electron microscope. This microscope maps out the structure at an atomic resolution, so it is extremely accurate. I actually have a video of the microscope instead of a picture because I could not find a good schematic of this. It's super expensive, so not many labs have this. So I guess it's best to just go for the person who sells it. They have a pretty good video. So this is just the housing, and it's later going to show the inside. So I'll let that play while I keep talking. Okay, so let's discuss how this works. The images produced are by electron transmission through the sample. So in order to do this, the microscope requires an extremely stable room environment. The microscope lenses are adjusted to create a focused convergent electron beam that probes at the sample surface. It is then scanned across the sample row by row, and the different signals collected are what form the image. These signals are caused by the sample interacting with the electron beam, and the information that is recorded is the morphology, which is the size, shape, and arrangement of the particles, as well as their relationship to each other on the scale of atomic diameters. It's crystallographic information, which is the arrangement of atoms and their degree of order, and also any atomic scale defects in areas. Let me move this. And also its topography, which are surface area features and how it looks in terms of texture, and its composition, which is the elements and compounds of the sample, along with the relative ratios in areas around 1 micrometer in diameter. So in figure C, this is an image produced from the chromium thiophosphate showing its layered nature. I think that's actually really cool that you can see each layer. The figure next to it is displaying how all of the elements are evenly distributed in the crystal sample. And underneath this is the quantitative result for the energy dispersive spectroscopy. The atomic percentage gives a ratio of 114, confirming the solid crystal growth from the chemical vapor transport method was successful. So these results are for the bulk chromium thiophosphate, but the most important process is getting it down into individual layers for application. Okay, so some of these slides were actually taken from a lab seminar I did at Los Alamos, mainly the background, motivation, and this one. And I had to include this LAUR number on it because this is data from the study. And although it doesn't seem that groundbreaking for this specific slide, the data is still technically government property. And so this code just means I'm allowed to share it with the public. Just a quick disclaimer. So I wanted to include this slide because I think it goes along well with the second portion of this production process. Because the second process is physical and doesn't require any fancy machinery, I thought it would be good to cover the physics of this process. I have here the trilayer, bilayer, and monolayer structures that I modeled in a software called Vesta. And this is showing that the calculation on the right included vacuum spacing, which was 19 angstroms of vacuum spacing. And this is to ensure no interactions occur when doing the calculations for the isolated layers. The energy that binds the layers together gives an estimate of how easily this material can be thinned down to its layered components from the bulk, and also tells us if this material is truly 2D. So the energy for both the trilayer and bilayer were calculated as the total energy of the chosen layered structure, represented as the N, minus the number of layers multiplied by the total energy of the monolayer system, then divided by the atoms per layer in the model of the chromium thiophosphate structure in Vesta, multiplied by the number of layers. And this is for normalization purposes. So you can see the bilayer interlayer binding energy is 36.2 MeV, and for the trilayer, 49.1 MeV. Both energy values are in the tens of MeV. This is less than 1 full electron volt. So this material is definitely suitable for layer extraction by the mechanical cleavage method. All right, now we can discuss the mechanical cleavage method, also known as the scotch-tape method, in which we can get the chromium thiophosphate down to its efficient 2D nature. So the mechanical cleavage method was developed back when a few scientists were trying to reduce graphite down to graphene. They were trying to formulate a way to do this that was more complicated than what was required. And then eventually one of them took a step back and went for a simple method. They took a pencil with graphite lead, drew a line over a silicone substrate, ripped off some scotch tape that was next to him, and proceeded to lift a layer from the substrate to the scotch tape. He took it to an experimentalist in his department who had later confirmed there was a single layer of carbon extracted from the pencil sample. And this scotch tape method actually won them a Nobel Prize. So now it is performed in a much more controlled environment with a little more formality, but it is still the cheap and easy scotch tape method that it is. Although it's a simple process, we can still walk through some of the physics and setup for this process. So the substrate used for chromium thiophosphate is a 285 nanometer thick silicon oxide. The sample must have a well-defined edge plane which will be orthogonal to the cleavage plane. Once placed on the substrate, the mechanical behaviors will strongly depend on the number of layers being extracted. So in the range of less than 5 layers, bending behavior from spontaneous rippling occurs. Homogeneous curving occurs around 10 layers of thickness, and kinking begins to happen at 20 or more layers. The force balance near the contact point can be used to calculate the specific surface energy of the monolayer, which is a direct measurement. And from the monolayer, the radii of a forced bent sample can be established, and determination of the reversibility without fracture can be observed. And this type of behavior is good for use in flexible electronics, such as mobile phones that are subjected to extreme folding conditions. So the picture on the bottom, the colored picture, this is an image of chromium thiophosphate extracted as 1, 2, 3, and 4 layers. The inset image is the scanned area for which this picture was produced by an atomic force microscope. However, to the right of the colored image, an electron microscope will actually show the molecular order of the exfoliated layer. The brighter spots belong to the heaviest atom, which is the chromium, and phosphorus and sulfur cannot be explicitly identified since they are so close in mass, but the earlier slide on composition ratio does show they were ordered correctly throughout the sample. Okay, now that we have covered the exfoliation process, we can talk about how the number of layers are identified, and this is done through Raman spectroscopy. And before getting into the setup and results for the layered chromium thiophosphate identification, I first want to cover how Raman spectroscopy works. So Raman spectroscopy belongs to the category of vibrational spectroscopy. It analyzes a sample chemically by using light to excite molecular vibration and then interprets the interaction afterwards. It is based on the inelastic scattering of light that occurs when matter is irradiated by light. As the change of wavelength is very small compared to the wavelength of the irradiated light, the change of the wavelength is most easily observed when using monochromatic light sources. After the monochromatic light has interacted with the sample, a very small part of it has changed its wavelength. And this is called the Raman effect, and the light is collected to gain information about the sample. So this process provides insight about the chemical composition, crystallinity, and polymorphism, contamination and defects, and thermal and mechanical exposure. So the Raman spectroscopy is set up starting with a light source focused on a notch filter, and the filter reflects the light beam to the sample at a right angle. The resulting Raman scattering is focused back to the notch filter. It serves as a bandstop filter where the incident light from the light source is nearly completely attenuated So only light with a different wavelength can pass through the filter unaltered. The measured light is redirected by mirrors to a monochromator, which uses grating to diffract the beam into a narrow band of wavelengths. The photocurrent from each wavelength section is then measured at the detector. In general, a charged coupled device is used to measure photocurrent into electric current. And the measured data can be saved and evaluated on a computer. And then for the spectro-electrochemical measurements, the target sample is used as a working electrode, and counter electrode completes the electrochemical cell. All electrodes are connected to a potentiostat, which is also connected to a computer. And both the spectroscopic and electrochemical data can be recorded simultaneously. So the figures on the right show the Raman spectroscopy data for chromium thiophosphate and its layered dependency. In A, this is showing the Raman spectra of the 1 to 5 layers compared to the bulk form, which the bulk has a thickness around 40 nanometers. This is shown as intensity as a function of the Raman shift. The high peak at 520 is actually due to the substrate, by the way. And these measurements were taken at its excitation wavelength of 514 nanometers. So this wavelength gave 17 Raman peaks and are organized alphabetically in terms of increasing frequency. For B, this shows the corresponding peak frequencies in which omega B is the upshift and omega L is the downshift recorded for each layered structure and the bulk. C is the difference between the modes represented as the omegas, and then D is the optical absorptions as a function of thickness. So you can see how each layer has their own unique response, and the layer amount can be identified through the line widths. The line widths become smaller as it approaches the bulk amount. There is a decrease in the line widths in the 2 and 3 layer, and this is due to substrate interaction because the material gets so thin. And hardening also occurs with increasing thickness in van der Waals interlayer interactions, even though the layers are weakly coupled. Right, so we've covered the entire process of producing this material. However, it sounds all very straightforward and simple to execute. So I think it is also important to cover the flaws in these methods because identifying the flaws helps us improve for better efficiency in the future. So there are some issues that can occur when growing these crystals. The most commonly encountered problem in CVT is the excess nucleation that leads to small crystal clusters and a slower growth rate. This usually occurs when a larger crystal is needed, and currently the way to address this issue is to use a seed crystal to suppress nucleation and include an inner tube to use as a separator and flow restrictor. And for chromium thiophosphate, this is not too much of an issue since only small crystals are necessary for study purposes. It's not being used in application yet. And then the mechanical cleavage method using scotch tape also has some difficulties and limitations. There is no particular execution of this technique that will guarantee a specific desired amount of layers, especially when trying to extract the monolayer. This presents a low yielding issue. Another issue is that the deposition onto a substrate when being transferred, there is a waste of material after the transfer since some of the flakes are still attached to the scotch tape, which will later be discarded anyway. And then the third issue is time. The entire substrate area needs to be scanned in order to find the amount of layers desired. So yes, the scotch tape method is cheap and easy, but this process needs some work to become more efficient for the exfoliation process. Okay, so that wraps it up for this project. I just told you some stuff. Now I'm going to tell you what I just told you. So we first started with some background and what are semiconductors and 2D materials, and also covered the motivation and application for 2D semiconductors. These materials are made through chemical vapor synthesis, and specifically for chromium thiophosphate, chemical vapor transportation, where this material actually doesn't even need a transporting agent and gives a high yield of 60%. We then covered how experimentalists use energy dispersion spectroscopy to identify if they've got the correct crystal growth. We then went into the exfoliation process for these materials, which is a quick and dirty cleavage method using scotch tape. From there, the number of layers can be accurately identified through Raman spectroscopy. And then lastly, we covered the inefficiencies in these methods. So if you made it this far, I congratulate you because I even barely made it this far. Actually, if you check the timestamp right now, you will see that I barely even made it past 25 minutes. So as a theorist, this was a struggle, but this was really good for me, really good exercise. So yep, I appreciate you listening to this, and I look forward to listening and watching everyone else's presentations. So see ya.